Hi children, we have been experiencing the COVID-19 worldwide pandemic situation. This situation is unprecedented and it forced us to stay at home. Yet, we have to keep ourselves engaged in our day-to-day academic works also. So I decided to come to you through few video lessons. This is my very first video lesson through the YouTube. Thermo Chemistry. Hope this will be very useful to you. Let's get into business. Unit 5. Energetics. Energetics is a branch of chemistry that deals with transactions of energy during chemical reactions. So where do we see an energy transaction in a chemical reaction? Remember, while a candle is being burnt, energy is liberated. Why do we burn a candle? In order to obtain light energy or sometimes heat energy. So in almost every chemical reaction there is an energy change. In some of the reactions heat energy is released, as in the case of a burning of a candle, for instance, energy is being released. But there are some other reactions in which we do not see a release of energy. Instead we see we have to supply energy to initiate the reaction, or in other words, in these reactions energy is absorbed. Why energy is absorbed? To initiate the reaction, right, or to continue the reaction. Take the decomposition of limestone, for instance, calcium carbonate. In order to decompose limestone, we have to put in energy, we have to supply energy. So during the reaction, energy is absorbed. The study of energy changes in chemical reactions is the scope of energetics or thermodynamics. Sometimes we call it as thermochemistry. So let's look at some basic terms related to thermochemistry or thermodynamics. Work and energy is our first interest. So what is work? A work is a movement implemented by a force. It might be a rotational movement or a linear motion. So whatever it is done by a force. We have to use a force to move something. What is energy then? Energy is the ability to do work. So we say sometimes we do not have energy to do work. What does it mean? We do not have the ability to do that work. So energy is the ability to do work. Both energy and work has the same units, that is joules, right? So how do we define the unit joule? Work done in the movement of a force of 1 Newton along a distance of 1 meter is 1 joule. So let's look at types of energy. Energy can be seen in different forms: mechanical energy, electrical energy, solar energy, chemical energy, etc. So there are many forms of energy. However, we should remember that all these types can be reduced to two basic types, that is kinetic energy and potential energy. So these are familiar terms for us even since our ordinary level studies. Now let us look at the kinetic energy. So what is kinetic energy? It is the energy acquired by an object due to its motion. Any moving object has a kinetic energy. Take an object with a mass of m, for instance. So it's moving with a certain velocity v. So what is the kinetic energy? So we equate half mv squared as the kinetic energy of a moving object with a mass of m and a velocity of v. Not only a moving object linearly, let's look at a pendulum. Pendulum shows a rotational movement. It is called a simple harmonic motion. So what is the energy related with a moving pendulum? Kinetic energy equals half I omega squared plus half mv squared. So what is the kinetic energy related to a gas under the pressure P and a volume V? So that is 3 over 2 PV, or we can say 3 over 2 nRT if it is an ideal gas. Now let's look at the potential energy. So what is potential energy? Potential energy is energy acquired by an object due to its position or arrangement of its components. Take an object with mass m in height of h from the reference zero level. So the potential energy can be given by the equation mgh. Our next interest is conservation of energy. So what is the conservation of energy? Energy can be transformed into other forms. So that is something we know very well. Energy can be transformed into other forms. It is a conversion of energy from one form to another. Here the energy is said to be conserved. There is no loss or gain of energy. The law of conservation of energy, or the first law of thermodynamics, says that the energy cannot be either created or destroyed. Now let us look at heat and temperature. What is heat? It is a form of kinetic energy. Heat is a flow of energy actually. Heat flows. Often it is said that heat is flowing or heat flows. Heat energy flows from a hot object or a place to cool object or a place. When we touch a hot object, heat flows into our hand and we burn or we feel hot. Then what is temperature? Temperature is a measure of kinetic energy. If the temperature of an object is high, the kinetic energy is also high. If the temperature of an object is low, the kinetic energy is also low. In other words, kinetic energy is proportional to the temperature. 100 milliliter of water at 35 degrees Celsius has a higher energy than 100 milliliter of water at 25 degrees Celsius. If water has a higher energy, its molecules move faster. So we have to remember that water molecules are randomly moving constantly, always, but these movements are happening more vigorously when the temperature is high. When the temperature drops, when the water cools, water molecules slow down. When the fast moving water molecules collide with higher energy on the thermometer, and its particles start to move faster. What are the particles in the thermometer? That is mercury atoms. Mercury column gets this energy from the moving particles in water, and it expands, showing a larger reading. So that is why we read a larger value when water is hot. Now let us look at heat change, delta Q. Now we can supply heat to water and increase its temperature. So let us consider an instance where heat energy is supplied to sample water to increase its temperature. The amount of heat taken or given out by water is proportional to the change in its temperature. Therefore, the change in temperature of water can be used to measure the heat exchanged by water. So here this equation is useful to us. Delta Q equals ms delta T. Here m is the mass of water, delta T is the temperature change, and S is specific heat capacity of water. So that is actually 4200 joules per Kelvin per kilogram. Heat change. So let us look at an example. Now we are going to supply heat to 25 degrees Celsius water in order to increase the temperature to 35 degrees Celsius. So what is the energy that should be supplied to increase the temperature from 25 to 35 of 100 milliliter of water? Now we can use the equation we mentioned earlier, delta Q equals ms delta T. So what is the mass m here? Mass is 100 milliliter equals to 100 gram or 0.1 kilogram. S is 4200, and the temperature change is 35 minus 25, that is 25 Kelvin. So I have written here as 25 Kelvin, but the temperature we have measured in Celsius, degrees Celsius. So it is obvious that the difference of temperature in Celsius equals to Kelvin also. Why? If we convert this 35 into Kelvin, we have to add 273. We have to add another 273 to 25. Then the 273 will be cancelled, and the temperature change delta T will be coming in Kelvin, but the value is the same, 10 degrees Celsius. So what is the answer? 4200 joule. So now as we calculated, 4200 joule should be supplied to 100 milliliter of water to increase its temperature by 10 degrees Celsius, right? So that is how we calculate the heat change, right? Now let us look at some technical terms we frequently meet in this unit. The first set is system, surroundings, and the boundary. So what is a system in thermochemistry? Now we have learned in our previous grades the term system. So we talk about the blood circulatory system, the digestive system, and urinary system, and so on in our body. Apart from that, we talk about the brake system in a automobile car. So what is a system? System is a part of the universe under our investigation, right? So that is how we have to define a system. That is how we can define a system, a part of the universe under our investigation, right? Then what is environment or surroundings? Everything else in the universe other than the system, or we can say that part of the universe that does not belong to the system. Part of the universe that does not belong to the system is environment. And then automatically comes to our mind what separates the system from the environment. So that is the boundary. Actually, you have to remember that this boundary is often a hypothetical line. A hypothetical line that separates the system from its environment is a boundary, right? Now look at this diagram. Our system is in the surroundings and the boundary separates it. And so what we get if we add the system to the surrounding? We get the universe, right? So this is little philosophical, because universe is made up of system and the surroundings. Types of systems is our next interest. Actually, systems can be divided into several groups. The first type is open system, a system that exchanges both energy and matter with the surroundings can be called as an open system. An open system like a beaker with some ingredients in it and it is not closed, so it is an open system. If you heat the beaker, the things in the beaker will be evaporated, or oxygen in air will be taken by the substance in the beaker and will be oxidized. So there is an exchange of substance with the environment, energy too. So an open system exchanges both energy and matter with the surroundings. But in contrast, a closed system does not exchange material with the environment. So think of a closed bottle or something, for instance. So energy can be supplied into this kind of a system. So there is an exchange of energy with the environment, but not matter. So what is the third type? Third type is a system that does not exchange either matter or energy with the environment. We call it as an isolated system, a system that does not exchange either matter or energy with the environment. So we can illustrate this with the diagram like this. So let's look at these diagrams that illustrates these three types of systems. Open system exchanges both matter and energy with the surroundings. A closed system exchanges only energy but not matter, so it is in red. The green color one is an isolated system. There is no exchange of matter or energy with the surroundings. And then we can classify those systems into two types, as homogeneous and heterogeneous also. So what are the homogeneous systems? A system in which all the substances are found in the same physical state is a homogeneous system. Let's take a solid, for instance. Solid kept inside the beaker. So the entire solid is in the solid state, a solid substance made of or a solution of a mixture of gases. A system in which all the substances are found in the same physical state is a homogeneous system, right? So the substance in the system is found only in the solid state or a liquid state or a gas, or in the gaseous state, or even in other states than the three major physical states. Then what is a heterogeneous system? A system in which all the substances are not found in the same physical state is a heterogeneous system. So take a liquid with its vapor, for instance. So there are substances in two physical states, liquid and vapor. So that is a heterogeneous system. Now we have to discuss the properties of a system. The properties of a system can be classified into two types: microscopic properties and macroscopic properties. So what are microscopic properties anyway? A system in the atomic or molecular scale can be called as a microscopic system. Properties in the atomic or molecular level should be determined by indirect means. We cannot measure them directly. We have to use some other way around. Kinetic energy of a molecule, for instance, or speed of a molecule, etc., and so on. So we have to calculate them. We cannot directly measure them. But the other type, macroscopic properties, these properties actually are things we can measure directly. For instance, volume of a system can be directly measured by using a glass instrument or something. We can measure. Temperature can be measured. Temperature of a system can be measured using a thermometer. Refractive index, color, surface tension, concentration, and so on. So those are macroscopic properties, and they can be measured easily from outside directly, more importantly. Macroscopic properties can be divided into two types, as extensive properties and intensive properties, right? Macroscopic properties can be divided into two types. So let us look at the extensive properties. Properties that depend on the size of the system: mass, volume, number of moles, internal energy, heat capacity, and so on. So these are things that depends on the size of the system. If the size of the system is large, its mass is high. If the system is small, mass is small. Volume is the same. If we take a sample of water, for instance, its volume depends on its number of moles. So these are the things that we can consider as extensive properties. There is another feature of these extensive properties. The value of the extensive properties is equal to the sum of extensive properties of smaller parts into which the system is divided, if we divide the system into say 2-3 portions, then if we add the masses of these small parts, we get the total mass of the body, right? So not only mass, all these extensive properties have the same characteristic. Okay, now let's look at intensive properties. Properties that do not depend on the size of the system can be named as intensive properties. For instance, density, temperature, refractive index, boiling point, melting point, etc. So these are qualities or properties of substances that do not depend on their size, right? Now another characteristic feature of the intensive property is if we divide the system into smaller parts, these properties are not being divided. For instance, density. If we take 100 milliliter of water, for instance, its density is 1 gram per cubic centimeter. Even if we take a very small portion of the water sample, say a drop of water, it should have the same density, 1 gram per cubic centimeter. So density, temperature, refractive index, boiling point, melting point, etc. Do not depend on the size of the substance or the system. And another important feature is if we divide two extensive properties, the properties we discussed earlier, extensive properties, if we divide two extensive properties, the answer is an intensive property. Take density for instance. Density, as said here, is an intensive property, but the equation of density is mass divided by volume. Mass and volume both are extensive properties. When we divide them, we get an intensive property, density. Others are also the same. Okay, and you can notice that if we write a property, if we write an extensive property as per mole or per gram, per cubic centimeter, per square centimeter, etc., we get an intensive property, right? So molar heat capacity is an example. Heat capacity is an extensive property, but molar heat capacity is an intensive property. Why? We mention it as kilojoule per mole. So if a unit is written as per mole, per gram, or per cubic centimeter, per square meter, etc., we can easily identify that they are the units of an intensive property. And our next interest is state of a system. The description of the temperature, pressure and composition of the system is said to be the state of a system, right? The state of a system means a description of the temperature, pressure, composition of the system, right? Properties, quantities with specific values for the state in which a system exists are called as state functions or state variables. Volume, temperature, pressure, composition or number of moles, density, refractive index, enthalpy, entropy, etc. are examples for state functions. For specifying a state of a system, it is not necessary to know all the state variables. Instead, it is enough, it is adequate to mention few of them. This is because all these properties are interdependent and only a few of them is sufficient to define the state of a system. So that is something you have to remember. Actually, the unknown properties can be calculated with some kind of equations. So that is something you have to remember. These properties do not depend on the history of the system, but depends only on the final and the initial state of the system. That is another important aspect of state of a system or state functions. State functions do not depend on the path of the change. Then let us look at a change in a state function. So these here are some more state functions here: enthalpy, entropy, and Gibbs free energy. So these are some more state functions. A change in such state function can be represented as delta H, delta S or delta G, and we can use these equations to calculate them. Delta H equals H2 minus H1, delta S equals S2 minus S1, delta G is equals to G2 minus G1. So this kind of equations can be used to calculate the change in a state function. So we will be using them later. Then we have to look at the path functions, not because they are important, not because of they are very important, but it is important to know them to have a better understanding about the state functions. State functions are more important for us in this lesson than the path functions. But let us look at path functions. Properties that depend on the path route are called as path functions. For instance, work done is a path function. Work done depends on the path actually, but in contrast, a potential energy difference is independent of the route. Potential energy difference is independent of the route. So that is a state function, but this one, work done, is a path function that depends on the route or the path. And then we have to look at the standard state of a system. Actually, state of a system is a description of the system in terms of volume, pressure, temperature, etc., as we mentioned earlier. The standard state is a very special state of a system. The pressure is a key thing here. The pressure is 1 atm at the standard state. Temperature is usually 25 degrees or 298 Kelvin, but it is actually not strictly adhered to this temperature. So temperature can be actually chosen depending on the requirement, but this pressure is important. Pressure should be 1 atm for the standard state. When solutions are involved, the concentration of the solution should be 1 mole per cubic decimeter for that substance to be at the standard state. So that is the end of the first lesson. Thank you very much.